This is an alternate proof of correctness of the RSA crypto system. In an earlier video, I showed a proof of correctness using a statement of Euler's theorem that utilized a multiple of Euler's phi function. What I'd like to do in this video is give a proof of RSA that relies on Euler's theorem as it is conventionally given. I will be assuming familiarity with the RSA crypto system in this video, so if you'd like to learn more about the basics of RSA, please do feel free to check out some of my other videos. Firstly, let's outline what we need to prove. Encryption in RSA relies on taking some secret integer message, denoted m, raising it to a publicly available exponent e, and taking the result of that exponentiation, mod a publicly available semi-prime n. This entire expression is denoted c for ciphertext message. Conversely, decryption in RSA relies on taking that ciphertext message c, raising it to a private decryption exponent d, and taking the result of that exponentiation mod n. The result of that expression should be identical to the original message m. So the question is, why is performing this exponentiation and taking the modulus result in m? This is, in effect, what we need to prove, that c to the d mod n is equal to m. So starting off with the expression c to the d mod n, the very first thing that we can do is substitute in m to the e mod n in place of c. So we have m to the e mod n all raised to the d power mod n. And we can do this just because of the way that c is defined right here. And so these two are equivalent. What I now posit is that m to the e mod n all raised to the d power mod n is equal to m to the e power raised to the d power mod n. To show this equivalence, let's make things a little simpler and call m to the e a. So I'll go ahead and move this over here. And rewrite what I want to prove over on the side here. So that is letting a be equal to m to the e, prove that a mod n all raised to the d power mod n is equal to a to the d mod n. Well, we know that a mod n all raised to the d power mod n is the same thing as a mod n times a mod n times a mod n, and so on, for a total of d times all mod n. And this is true just by virtue of multiplying things out. So to figure things out from here, we have to know that in modular arithmetic, there exists this property that says that for integers x, y, and z, x mod z times y mod z all mod z is equal to xy mod z. I'll go ahead and offer a quick proof of this statement here, but if you're more interested in the main proof, please do feel free to skip ahead. Let's consider something like 27 mod 7, which we know equals 6. Well, what's another way to express 6 using 27 and 7 but not the modulus operation? Well, we can say that 6 is equal to 27 minus 7 times some integer t. So 27 minus 7t is equal to 6, and in this case we know that t is equal to 3. Well, we create this sort of expression for any integer mod another integer. In fact, any a mod b is equal to a minus bk for some integer k. So instead of x mod z and y mod z up here, we can call this x minus zk1, and we can call y mod z y minus zk2 for some integers k1 and k2, and all of this mod z. Multiplying this out, we get xy minus xz k2 minus yz k1 plus z squared k1 k2, and all of this mod z. Now we can separate out the z terms. So we have xy minus z times xk2 plus yk1 minus zk1 k2, and once again all mod z. Now we can eliminate multiples of z when we take mod z. So that's going to eliminate this entire expression because it's z times a quantity. So we're left with xy mod z, which is precisely what we needed to show equivalency to up here. So now using this property, we can go back up to our original proof and apply it here. Since we're multiplying a mod n by itself d times, we have that a mod n times a mod n d times mod n is equal to a multiplied by itself d times mod n. And so substituting m to the e back in for a, we have that this is equal to m to the e all raised to the d mod n, which is precisely what we were trying to show. And so now we can say that m to the e to the d power mod n is of course equal to m to the e d power mod n. Now for the next part of our proof, we need to find an alternative way of expressing ed. Now, if you're familiar with RSA, you know that d is chosen such that ed mod phi n is equal to 1. Therefore, we can say that ed is equal to 1 plus k times phi n for some integer k. I'm not going to go into why you can express ed this way, but it's pretty much the same logic that we were using earlier to express x mod z and y mod z in different ways, except now we're isolating the dividend, ed, instead of the remainder, which is 1. I go more into the logic of why ed can be expressed this way in an earlier video, so do feel free to check that out if you want to see why we can say that ed is equal to 1 plus k phi n. Now I can easily substitute in 1 plus k phi n in for ed here, so I have m to the 1 plus k phi n mod n. I can then say that this is equal to m times m to the k phi n power mod n, just by properties of exponents, and that this in turn is equal to m times m to the phi n to the k mod n, again by properties of exponents, and that this is equal to m times m to the phi n mod n, all raised to the k power mod n. And this comes from using this property right here and substituting in m to the phi n for a and k for d and letting n remain the same. And so now comes the real crux of the argument, for which we use Euler's theorem. And that is given as follows. For any two integers a and n, such that the GCD of a and n is equal to 1, then we can say that a raised to the phi n power mod n is equal to 1. In m to the phi n mod n, we know that the GCD of m and n is equal to 1 because this is stipulated when choosing a secret integer message m. Thus, we can conclude that m to the phi n mod n is equal to 1 by Euler's theorem. We then have that this is equal to m times 1 to the k mod n, which is of course equal to m times 1 mod n. And 1 mod n is of course equal to 1, so we have m times 1, which is of course equal to m. And so now, going all the way back up here, we can conclude that here c to the d mod n is equal to m. And this concludes our proof. Well, as always, I hope this was helpful, and thank you for listening.